The fourth talk of this session is entitled Raising Expectations, Automating Expected Cost Analysis with Types. Dee Wang and David Kahn will present the talk together, and they will tell us about a type-based analysis of driving upper bounds on the expected execution cost of probabilistic programs.
Hello SFP and future viewers of this video. My name is Steve, a PhD student at Carnegie Mellon University, and today my co-author David and I are going to be presenting our work on automatic probabilistic resource analyzing language from our paper, Raising Expectations, Automating Expected Cost Analysis with Types, which is accompanied by an implementation we call PRAML, standing for Probabilistic Resource Aware ML. Resource analysis of programs is something that is of renewed interest in the modern day. Not only does it fulfill the traditional role of identifying performance bottlenecks, but also the following. If you care about digital security, you will need timing analysis to mitigate side-channel timing attacks. If you want to take advantage of the latest tech trends in smart contracts, you will need to be able to measure your gas usage. And, of course, if you care about our real world, it will sure help the climate to be able to consider the carbon footprint of the code running in data centers. There are just so many different resources in so many different programs. So the problem is that nobody has the time to go through and formally analyze all of them. For this reason, our work builds upon an approach of language-based automatic resource analysis. In Primal, a programmer may code as per usual and just via type inference receive verifiably sound resource analysis at their fingertips. Now, so far, all of this already exists in Primal's predecessor, Resource-Aware ML or RAML. However, Primal can model something that RAML cannot, probability. Probability is increasingly important in modern algorithm design. Randomized and statistical algorithms are employed on mass data constantly to squeeze out every bit of efficiency. So it is crucial that modern resource analysis systems can cope with expected costs rather than just worst case. This is where our work on Primal comes in. Primal extends the worst-case resource analysis of RAML to measure the worst-case expected value. It is worth noting that the resulting language is also suitable for probabilistic modeling, and we will discuss a couple of these applications later on. Now, I leave it to David to talk about more about the meat of our work.
Thank you, Dee. Let's start by quickly going over how type system-based resource analysis works in a non-probabilistic setting. We will be using RAML's Automatic Amortized Resource Analysis Type System, or AARA. The idea of AARA is based on the potential method of amortized analysis set out by Robert Tarjan. What we are going to do is imbue the types at each stage of the program environment with some notion of potential energy, and allow the energy to change over time. The changes in potential energy between each step then describes the energy discharged to pay for costs. The key takeaway is this. The total potential needed at the beginning is an upper bound on the total cost. So, by typing the program with this notion of potential energy, we've bounded the cost. And AARA does this while still maintaining the compositionality of a type system. This technique even works for higher order functions and polynomial or exponential cost bounds. However, let's start small and make an example of the mem function, like that from the OCaml standard library list module. We will use AARA to bound the number of recursive calls. So here is a version of the mem function. Now, the mem function takes the naive approach of checking whether the argument x is in the given list. It iterates over the list, checks each element for equality, and returns true if it ever finds one. At worst, we might need to check the whole list, which means we could expect n recursive calls in the worst case, where n is the length of the list. We can show this using the potential method as follows. First, we explicitly mark the costs where they occur using tick operations. That would occur right here at the recursive call. Then we can type the list argument with 1 unit of potential per element, written like so, with a superscript 1 representing the amount of potential per element. This aligns with what we've just guessed the worst case cost will be, the length of the list. Then we can write the type of the whole function with this, where these numbers here on either side of the arrow represent the resources present before and after the function call. In this case, we can just let them be 0. Now let's move on to the interesting parts in the function body and see how we use these types with potential and how we match up with the function signature just provided. We first deconstruct the list, gaining the 1 unit of potential that was previously stored at the head of the input list. Then, if the head is the element we're looking for, we can just return true and drop all the remaining potential. Otherwise, we use that 1 free unit of potential to pay for the tick expression, and then recurse on the tail of the input list. To perform this recursive call, we check the potential in the current environment against the function signature. Because the mem function requires 1 unit of potential per element in the list, and the tail of the input list still has 1 unit of potential per element, this line type checks. And that's it. The potential we guessed at the beginning, 1 per element in the list, is the worst case bound we guessed, the length of the list. As a final note about this example, although we did it by guess and check, these types actually can be inferred. This is because all the relevant arithmetic we did to calculate these constants can actually be given via linear constraints. If we collect the linear constraints and solve them, we get our desired resource bounding type. This continues to hold for Praml in general as well. Now, the language we just saw is a subset of OCaml and non-probabilistic. So to make expected values at all meaningful, we extend it with what is probably the most primitive probabilistic operation possible, the coin flip. Specifically, we flip a coin to decide which branch of code to run. We can slot this new behavior into the RAML type system with some pretty intuitive rules. The flip rule deals with coin flip expressions, where the coin bias is a constant. In this rule, gamma is a typing context, Q is the initial amount of resources, A is the resource annotated type of the expression, and of course, P is the coin flip bias. So what this bottom part says is just that the flip expression type checks as A under context gamma with Q extra resources. The key idea of the flip rule is that the expected cost between the two branches, E1 and E2, can be calculated as the weighted sum of their respective typing judgments. And you can see here and here that we perform some sort of weighting by the flip probability P. We also allow for a more complicated case, where the coin bias is parameterized, as if it were a program variable. It turns out, in our implementation, that these two rules can be treated as special cases of one more general rule. However, despite the intuition behind these rules, they posed a problem. While these type rules do indeed turn out to be sound, the probabilistic nature of the new flip operations are incompatible with the operational semantics used in RAML's AARA. However, we need an operational semantics in order to show that the resource analysis is sound. To overcome this, we created a whole new operational semantics for Praml based on Borgstrom et al. 2016's trace-based and step-indexed distribution-based semantics. You can find the details of this adaptation in the paper. With operational semantics in hand, we can state soundness as follows. If expression E types as A under context gamma with Q units of initial potential, then the expected cost of evaluating E is bounded by Q plus the potential in gamma. This soundness statement should seem familiar. It is exactly the key takeaway of the potential method mentioned earlier. The initial potential bounds the cost. This holds even for programs that may not terminate. We can also say that if the cost model counts evaluation steps, then the existence of any expected cost bound at all implies almost sure termination. Now let's look at this new type system in action on a simple example. Here is the program Bernoulli, which performs a sequence of Bernoulli trials. When run, it has a 50% chance of recursing and a 50% chance of terminating. As many might remember from their Intro to Probability course, this results in a geometric distribution with expected value 2. Thus, while it could go on forever, we can actually give it a finite notion of cost. Let's check it now using Praml. Now, the only initial potential that Bernoulli needs is 2 units. 1 unit of potential is spent immediately on the tick. After the coin flip, we assign 0 potential to the head case because it returns immediately, and 2 units of potential to the tails case. Then in the tails case, we reuse the guessed type of Bernoulli, and it all works out. Because the weighted sum of the potential assigned to these 2 branches is exactly 1, the flip rule justifies going into these branches with only 1 unit of potential, even though the tails branch by itself would require 2. In the paper, we use this same automated technique on a variety of more complicated functions with more interesting resource bounds. For instance, we show that Praml can analyze the gambler's ruin, wherein 2 players, Alice and Bob, continually bet $1 against each other on the results of a coin flip until one player runs out of money. In the program, we model the amount of money as the length of a list. If the coin is fair, Alice starts with A dollars and Bob starts with B dollars, then this series of bets is expected to take A times B rounds. Our implementation infers this bound exactly. Praml can also infer non-trivial bounds with parameterized probabilities. The von Neumann function implements a mechanism to make a fair coin from a biased one. With some scaling trick, Praml derives that the function is expected to take 1 over p times 1 minus p steps, where p is the probability for the biased coin to show heads. Both of these examples also show that Praml can be of use in probabilistic modeling, as these are both probabilistic models. Here are some tables of various other analyses of probabilistic models from the paper. The bounds themselves are of various complexities, but one nice takeaway is that the time taken to analyze these programs automatically is usually well under 1 second. This is good because real-world analyses need to run in a practical time frame. Now let's talk about some more empirical probabilistic modeling. Look back quickly at Mem and Bernoulli. If you squint a little, you might notice that Mem behaves a lot like Bernoulli, possibly terminating at each iteration. In fact, if we say that equality holds with 50% chance, then the runtime profiles of these 2 programs are pretty much the same. And note, the constant expected cost of 2 from Bernoulli is far better than the linear worst-case cost of Mem. This opens up another avenue for analysis using probability, approximating deterministic branches with probabilistic ones. If we can empirically determine that some code branches with a given probability, we can approximate it with a flip and use the Praml type system to get a better sense of the actual resource usage. In our implementation artifact, we include a mode for doing this, and we include some results of its application in our paper. For instance, insertion sort achieves linear time complexity on nearly sorted data. That's all I have. I now leave it to Dee for the close.
Thank you, David. In summary, in this paper, we have developed a probabilistic extension to the ARA type system. We overhauled the operational semantics to provide sound. We also implemented the result and applied it back to deterministic programs with empirical statistical techniques. In the paper, we also give one more application about automatic analysis of sample complexity. That is all we have the time to talk about, and thank you for listening to our talk. Stay healthy, and hopefully we can talk in person the next year.
Thank you, Dee and David. If you are watching this talk live, please don't forget about a Q&A session that may be available in your time band.